You ready?
Yeah, I'm good to go.
Brilliant. We started the recording. The stage is yours.
Fantastic. So thanks to everybody for dropping in for this extracurricular lecture. So I'm going to give an introduction to how we model some details of ice sheets. And in particular, I'm thinking about these very large continental scale ice sheets that you find in Greenland and also in Antarctica. So this image here that we see at the bottom is a false color reconstruction, but intended to show the Antarctic continent. And also there's an ocean fringing it. So as well as the ice sheet that's formed by collation of snow on the top of the Antarctic continent, there's also a little bit of what's called sea ice around the edge. So I'm not going to focus at all on that today. That's another very interesting topic. But we're going to focus on ice basically perched on top of the land in Antarctica and Greenland and try to understand some features of that. So I'm going to start out by giving a fairly broad brush motivation and picking up some key features of ice sheets. So the initial part of the talk is going to be quite phenomenological to set up the particular processes we're interested in understanding in the particular phenomenon and give a little bit of motivation. But then a bit further on, I'm going to step through and derive a simple model of ice sheet flow and use this to understand something about the dynamics and point towards processes that we don't understand as well. One of the things this will lead us to consider is looking at thermodynamic drivers of ice sheet decay. And I'll very briefly touch on marine ice sheet instability on the end. So I don't think I'll have time to go through the mathematics involved in this, but I'll give you a physically based description of how an instability might work with ice sheets. Okay, so there will be a little bit of technical grist that will come in the middle. So we'll step through and we'll put together a model of ice sheet flow. Essentially, you don't need to know much more than a little bit of manipulating differential equations and a little bit of multivariable calculus. So we'll pick things up as we go through. Some of this will resonate. If any of you have seen some fluid mechanics, there'll be some resonance with some of the topics in there. But I'm going to step through the processes in a way that won't directly use fluid mechanics. So we're going to pick up the principles just by thinking about the mechanics of the system. Okay. So we're going to start off by thinking about the Greenland and Antarctic ice sheets. So we got on the left here this reconstruction again of the Antarctic ice sheet. On the right is actually a visual color image from the NASA MODIS sensor and satellite data set. So if you go to NASA Worldview, you can see these beautiful images when there's no cloud. Sometimes you have to work quite hard to find an image without the clouds over the top. But you can see basically the Greenland ice sheet in here. And just for scale, you can compare this to, you've got Norway over here and the UK down the bottom. So you can see you've got a relatively large region that is covered in ice and snow. So we're interested in phenomena that occur on length scales of up to thousands of kilometers in the horizontal. These ice sheets can also be relatively thick. So if you were to go to the middle of the Antarctic ice sheet, there would be places where the thickness of the ice is approaching 2 miles in thickness. So a few kilometers in scale, so thousands of meters in scale. But this vertical thickness is much smaller than the horizontal extent. So when we're coming to describe these ice sheets later, we're going to be thinking about relatively thin films of ice and how they evolve. And just to give you an idea of one of the motivations for interest in understanding ice sheet flow, this comes from thinking one of the key drivers is an interest in understanding contributions to sea level. And if you were to completely melt the Antarctic and Greenland ice sheets, you'd be able to raise sea level by around about 70 meters. So one of the current drivers of a lot of modern research on this topic is trying to build some understanding of what kind of changes are likely over the coming century or so. But also understanding how ice sheets might have changed in the past. And from my own perspective, it's also a pretty cool fluid dynamics problem also too. So there's some nice, interesting physics wrapped up in that. Okay. So how has this mass balance been changing? So I'm just, by way of motivation, I'm just showing you some plots of measurements of how the mass of the Greenland ice sheet has changed over recent years. So these come from clever satellite measurement technology. So there's the GRACE satellite, or it's actually a pair of satellites. So it's actually able to act a little bit like a weighing scale and estimate the mass of ice and water and its distribution by basically picking up very subtle changes in the gravitational field. So you get these two satellites that orbit around the Earth, one chases the other. And by looking at small differences in the acceleration and the differences in their separation, you can start to back out with quite a lot of inverse modeling what that means for changes in mass on the orbit path below you. So this technique has been used to basically weigh the mass of the ice sheets and to see how they change. You have to do a little bit of work to subtract out things like bedrock and ocean fluctuations too. But what you're seeing in these plots is change of the mass relative to some baseline. So 0 is basically taken as the mean of the time series in here. And you see that there's a lot of fluctuations in this. So there's some sense of a seasonal cycle in the Antarctic ice sheet, and it's more marked in the Greenland ice sheet. But you've seen in recent years, there's been an overall mass loss from both the Antarctic, but perhaps more significantly at the moment from the Greenland ice sheets. So to give you an idea of how significant this is looking at masses in gigatons of ice. So you can do a simple calculation, but I'll save the time on it and just give you the answer. To convert this into equivalent sea level rise, so using the fact that the oceans cover about 2/3 of the Earth's surface, if you run through that calculation, these kind of scale of ice losses are actually only equivalent to giving you a few centimeters per decade of sea level rise. So perhaps something not too dramatic just from the ice sheets. But there's some evidence that people have put together from information about past climates. So digging up things like sediment cores and looking at where the sea level would have been based off certain organisms that you'd like to live near the sea surface. This evidence suggests that there was considerably faster sea level rise than this during the past 20,000 years. So a factor of 10 or maybe even 100 or so faster. And so one of the uncertainties is we'd like to be able to understand whether this fast sea level rise might be possible in the future. And this is probably a question that we can't answer with great certainty yet. So we can make a prediction based off our best knowledge of the system, but it's one where there's substantial physical process uncertainty that's quite hard to constrain. Right, okay, so before we dive into details of modeling ice sheets, I just thought I'd say a few words about how does an ice sheet work in terms of its mass balance, and just give you the broad picture. So there's various pieces of this picture. So I'm going to give you a very idealized cartoon sketch just to give you an idea of the processes involved. So you accumulate mass in the center of the ice sheet by snowfall. And then that ice flows out towards the edges of the continent, towards regions of lower surface elevation. And we'll understand why that happens a little bit further on. You can also lose mass by melting on the surface of the ice sheet. So after that ice has flown down to lower elevations, you might encounter warmer temperatures near to the surface. and that can give you surface melting. You can also have some sublimation going on too. Another key process that we'll dig into a little bit is the ice sheets in some places are able to interact with the ocean. So you end up with these floating tongues of ice, basically where you have an ice, what's called an ice shelf floating on top of the ocean water. And then this can either melt into the ocean, or the other thing it can do is it can fracture off icebergs. But the whole system is basically a little bit like a production line where you're putting in snow at the center, the ice is flowing out towards the edges, and then you're losing mass out into the ocean. And this is something that happens perpetually whilst you're in an ice-covered state and you're accumulating snowfall in the middle. But there can obviously be oscillations on this according to how you force the ice sheet. And so this image at the bottom just gives you an indication of how the velocity in the ice sheet is changing over time. So it's changing with spatial position, or actually, technically, it's only showing you the speed. But you can see regions. There are these very fast flowing regions where the color bar gets up to, so the purple and blue end of the scale are ice speeds where it's moving at kilometers or more per year. And these can be found near the fringes of the continent where the ice is starting to flow into these floating sections of ice, whereas there's much slower flow in the interior. So there's also been a key interest recently in understanding these relatively fast flowing regions of ice. Okay, so just to pick up a little bit, give you a feeling for the order of magnitude of some of these terms. So on this particular plot, so this is a plot from the Intergovernmental Panel on Climate Change 5th Assessment Report, where it was trying to estimate various contributions to that mass budget. This is a case for Greenland rather than Antarctica that we were looking at before. And you can see that, so there's some variation in the surface mass balance. And one of the things that comes out of this is if you look at the rate of accumulation of snow, you can end up with, you would basically end up, in order to replenish an ice sheet that had been lost by melting at the edges, if you were to just wait on the characteristic snowfall rate in the center of the continent to build this up, you'd have to wait thousands of years in order for that ice to discharge out into the ocean. And in fact, it takes even longer than that because you've also got this ice flow too. So we've got this flow of ice from the center of the continent out towards the edges where it flows out into the ocean. And one other thing that you can pick out from satellite measurements, so this, I should have said, this left-hand panel comes from a combination of meteorological data, and then this is post-processed through an atmospheric circulation model to try and predict the precipitation or the surface mass balance. These other two right-hand plots come from satellite imaging. So the ice flow speed will come from things like tracking surface features and where those surface features move between two successive images. And then also using laser altimetry, you can see how the surface is going up and down. So they bounce lasers off the surface. And you get this crisscross grid due to the overpasses. But you basically see the most dynamic action in Greenland, at least. So the most substantial thinning seems to occur. So it's mostly along the coastal regions, but in particular, these coastal regions in basically northwest and southeast Greenland are the ones with the most significant thinning going on. Right, yeah, okay, so we've seen all of the various different components just to give you a little bit of context on how this system's behaving. So what I'm going to do now is I'm going to step through and explain how you would derive an ice sheet model and what the relevant forces and are driving the flow. But first of all, we're going to focus on the mass balance. You could do this using by solving the Navier-Stokes equations for fluid flow in 3 dimensions, and then you could force those with the putting mass in at the surface due to the snowfall. And people do this computationally. This turns out to be a very computationally intensive problem. So something that's quite challenging to solve numerically, to solve the entire three-dimensional circulation. So I'm going to introduce you to a different modeling approach here that's often used for making very long timescale predictions over centennial or millennial timescales, or even hundreds of thousands of years. So to make the model a bit more computationally efficient, from a numerical modeling perspective, if you could have a 2D grid of points to solve for, that's a lot less computational work than solving in 3 dimensions. So we're going to build a model that has that particular type of feature. And it's going to be a model that's going to work with, basically, we're going to be thinking about flow in 2 horizontal dimensions, but we're going to be thinking about the depth integrated flow, or thinking about average quantities over the depth of the layer of some thickness h, and how this evolves. So I'm going to step through and illustrate the pieces using a effectively a 2-dimensional setting for all of the little arguments I'm going to put together, where things are only varying in x, but you can generalize this out to describe flow in 2 full horizontal dimensions, and then the thickness changing in the vertical. Right, okay, so we're going to think about this slice of ice. So we're going to take a little element of ice that has thickness that goes between x and x plus delta x. I'm going to assume the ice has a constant density, rho I. So for those of you who've seen some fluid mechanics, I'm basically going to assume the ice flow is compressible, and then I can treat concepts involving conservation of volume and concepts involving conservation of mass interchangeably. So that is a little bit of an approximation when it comes to thinking about the snowfall, but it's going to help us pick out the key ideas. And if you haven't seen the fluid mechanics, you can just think about, because the density is constant, a certain volume will have, or as the volume changes, there will be, the mass will change by a factor multiplied by the density. So this little segment of ice, we're going to be interested in how the quantities change within this little ice segment. And we're going to, in principle, we're going to allow for there to be snowfall on the surface. But one of the key things that we're interested in that controls the rate of change of thickness of the ice sheet is going to be related to how the ice flows around. So the ice in general could deform as a viscous fluid, but we're not going to worry about the fine details of that in our depth integrated model. We're going to think about volume flux of ice. So if you're interested in a volume flux moving to a particular region, I'm going to use U here for velocity out of years of habit. We're basically going to be interested in the ice flowing into a particular region. So with some velocity U, in general, this could depend on Z, but we're going to think about the flux that's averaged over this face over to the left here. And when you calculate the flux across the surface, you're interested in the normal component of velocity integrated over the surface. And then that basically involves integrating from the bed all the way up to the surface. So Z is B up to Z is eta. The sketch I've drawn, this bed is flat, but the ideas that I'm stepping through here will carry over to cases where there's also bed slope too, provided it doesn't vary too quickly. So, and then you multiply that, so that's giving you the height, and then you've got the width of out of the plane. So where I use W here, this is, or delta Y, this is going to be width out of the plane. Oh, and that should be integrated over Z. Okay, sorry, there's a little typo in there. Okay, good. So if you integrate the horizontal velocity over Z, so over the thickness, that gives you basically the flux of the ice. And then if you think about how much the volume of ice, or equivalently the mass divided by the density, is changing within this region, you can have a change in volume. So the length of the box times the change in the height, because we fixed the length of our box in here. That can either change due to accumulation of snow on the surface. So you've got snowfall accumulating across the entire width of the box. You have ice flow in on one side, and that tends to increase the volume of ice in the box, but then you have to subtract out the ice that's flowing out on the other side. So this mass flux or volume flux cube at x plus delta x. And then if you do the classical thing, so you've probably seen this kind of argument before, if you're thinking about a small box and you think about changes over an infinitesimal volume, so a small difference in x, and you take the limit that delta x goes to 0, you basically end up pulling out a continuous conservation law. So you basically end up picking up something where you've got dh dt, so the rate of change of thickness is driven by the net accumulation at the surface. So you can add snowfall that will tend to increase the thickness, or you can melt. But the other key factor is you can have a divergence of the ice flux too. So if you've got more ice flowing in than is flowing out, you'll tend to get an overall thickening because you've got a convergence of the ice flux or a negative divergence. And this basically carries over. If you do the same argument, adding the extra dimension in and allow ice flow in 2 horizontal dimensions, you get the divergence of a horizontal flux instead. Okay, so we've got a mass budget for our ice sheet now. So in principle, if we said from our atmospheric model, we know what the snowfall is, or we know what the surface melt is. So if we knew the flux of ice, we would now be able to calculate how the thickness changes, and then you've got a completely closed model. But we need to come up with a way of predicting the flux, and then that's going to depend on the velocity integrated over the depth. So how do we figure out the velocity driving the flow? So if we think initially about the forces involved, so one of the really key forces is due to the weight of the ice in this system. However, if you think about resolving components of forces, and you're thinking in a setting where the surface of the Earth is locally flat and is in the horizontal, your weight due to gravity is only acting in the vertical direction. So we need a horizontal force in order to drive this horizontal spreading of flow. And this kind of flow is a little bit similar to if you did something like pouring a drop of honey onto a plate or something similar, or pour a very small amount of water onto a surface, it will tend to spread and spread out laterally. And this is something that is quite easy to understand on energetic grounds, because you're reducing or you're releasing your potential energy, and as it spreads out and occupies a relatively smaller height. But we're going to try and understand this using the force balance and how we can produce a horizontal force. And the key ingredient that you need is you need to take account of pressure forces. So some of you may have seen this argument in courses about calculating hydrostatic pressure. If you haven't, the basic idea is, so you're hopefully familiar with the concept of pressure. So it's basically giving you a force per unit area, and it's something that acts isotropically. So a pressure on, if you've got constant pressure, you basically get an isotropic force in all directions. But one of the things that you can pick out in these systems is you can calculate what kind of pressure field you would have if you only thought about the weight of mass of ice. So if we take a small little cube or square of ice in here, or sorry, cube of ice, we can think about the force balance in here. And if this ice was not accelerating, and because this layer is fairly thin, the vertical motion is actually turns out to be fairly small. So there's not much acceleration in the vertical. And in the simple description we're using here, we're also assuming there's not much viscous force also acting in the vertical. So we're going to consider a case, and this turns out to be a reasonably good approximation even for real ice sheets. we're going to consider a case where we've got a balance between the weight of this box of fluid, so G times the density of ice, times the volume, so this area, cross-sectional area dA, times the thickness of this particular volume. And that weight is a downward force in this particular sketch. And then that's going to balance the force due to the pressure acting on the surface. So where you have pressure below, so if you calculate the pressure at the bottom of the box, so it's Z, and then sum that over the area, you're going to get an upward force on the bottom surface of this box due to the pressure. And on the top surface, the pressure may have changed slightly, so you're at a new height Z plus dZ, but you're still acting over the same area, and then you would get a pressure force pushing downwards onto this box. And if you balance these two pieces, so you basically balance the pressure force upwards on the bottom, the pressure force downwards on the top, so summing pressure over the area, and then that balances the weight or the weight of the object. You can set up a force balance that looks in the following form. So the pressure at the bottom, the pressure at the top, both multiplied by area, and then you've got the weight of this cube of fluid. And if you do the same little trick that you did before, where you've got a difference in pressure over a small distance, if you divide by dz, you can approximate this by a partial derivative, so a gradient in the z direction, and you get that there's a gradient in the pressure is balanced basically by the weight of the fluid per unit volume. So you get this pressure gradient balance as the density times gravity. Here. So this is something called a hydrostatic balance, and this is really key to understanding the dynamics of these ice sheets. So we're going to take that now, and we're going to think about now this layer of ice that we're going to assume is able to deform and flow, but it's going to deform and flow as a result of the pressure acting on the surface of the ice sheet and also on the interior. So we can take this equation that tells us that there's a, in the vertical component of the force balance, you've got the gradient in pressure in the vertical direction, balances the weight force. So dp dz is minus rho ig in the ice. And actually the same thing actually also holds, but just replacing the ice density with the atmospheric density once you're above the ice surface. So what you can do is if you integrate from the upper surface of this box, so if we come up with some level Z is capital H, where we fix the pressure, and you integrate down to the bottom, you end up and you enforce your boundary condition that you fix that the pressure is 0 at Z is H to fix the constant of integration and do a little bit of rearrangement. You find that in the ice, so below the surface, Z is eta of this ice layer. You get the following equation for the pressure. So you've got the pressure is the constant value at height H. Then you get a contribution moving downwards from the weight of the air sat on top of the ice sheet. So it depends on the thickness of the air column H minus eta and G times rho A, the density of the air. And then you also get a contribution due to the weight of the ice down to the particular level that you're sitting at. So we've now got pressure at any given Z level in the fluid, so any particular height. And now if we want to calculate a horizontal force, we can see that this is what's going to give rise to our force. So we're going to get a force due to there being different amounts of air or ice sat on above you in this particular column of fluid. So you end up with slightly different pressure in different locations depending on how far you are below the surface of the ice. So if you run through and look at the relative differences, the key part of this is you end up getting a change in the pressure. The thing that changes from one point to the other is as you move to slightly different surface elevation, you're picking up a different fraction of air versus ice. So that has a different density, and so gives rise to a difference in the hydrostatic pressure. So you get this difference in the hydrostatic pressure that depends on the density difference between the ice and the air. It depends on gravity, and it also depends on what I'm calling delta eta, is the change in the free surface height of this, the top of the ice sheet. So this means, in general, if you're interested in pressure gradients, which are going to be key, we're going to see in a second for driving flow. So the horizontal pressure gradient, it's going to depend on the density difference between ice and air, gravity. But the key thing here is the thing that's going to vary in this particular flow is the surface slope. So you get a driving force from the pressure gradient that's linear in the surface slope. And that's one of the key driving forces for the flow. Okay, so the last little bit of this calculation is we're going to step through and take that expression for, we said that the pressure gradient is going to provide a driving force, because if you have higher pressure on one side than the other, that's going to force the fluid or force the ice from left to right. Just you get a force from the pressure gradient. And I should mention, so this is a force per unit volume. So the densities in here, rho I and rho A, are the mass per unit volume. And then this is the force per unit volume. So we're going to just put together the total picture for the force balance on this little infinitesimal slice of ice. So we've got high pressure to the left, low pressure to the right. So that's going to push the ice to the right. We have some resistance to the flow. So this is resisted by the basal drag in this particular description. So I'm going to describe this with something that I'm going to call basal stress tau. So this is basically the drag force per unit area over the surface of the bed of the ice sheet. So stress is a force per unit area in all of this. So that's trying to slow things down. And I'll just give this a general form tau in now. It could depend on a whole manner of different things, but we'll just give it a general form to think about the force balance. So we can think about applying Newton's second law to the flow of this ice sheet. So you're good with Newtonian mechanics for ice sheet flow. So we take the volume of our little piece of ice, so this is dx dy and h, the thickness, and multiplied by the density of the ice. The changes in the thickness are going to give you a second order effect. You multiply this by the acceleration of this small element. So that's mass times acceleration on the left. On the right, the forces are that we saw before, is you've got a pressure force, and then that's now acting, and you're summing over the whole surface. So there's a little distance dy into the page, but there's also the height of the fluid. So that's giving you your surface area, this h dy in here. And you've also got the pressure force pushing back in the other direction. So there's differential in pressure. So you've got P plus delta P. And then the ice thickness can also have changed as you move to a different location. So I should mention, as I've drawn this, delta H is actually negative in this particular picture. So you've thinned the ice out, and that actually means that the pressure is also going to be lower. So delta P is negative as drawn. There's a little component due to the fact that the surface is actually sloping. So you get a component from the pressure acting on the surface. So it's basically proportional to sine of the angle. And you just need to include this to make sure the next equation I write down works out. And then you've also got the basal stress acting on the bottom. So it's force per unit area, and then multiplied by the area of the little element. And we're going to do our continuum limit again. So divide by dx dy, and then delta x delta y, and then let those go to 0. And as you do that, you find that you if you also use a shallow angle approximation to pick out the normal in here, you end up with the following force balance. So this term in here ends up cancelling, so you don't have a dh dx term. It's only changing due to, you're only picking a multiple of h in here. So you get the acceleration, you've got this pressure gradient driving the flow due to the surface ice slope. Interestingly, it only depends on the surface slope because it's only depending on the weight of ice below the surface. So you don't care about variations in the bed topography for this pressure gradient. But because you're integrating that over the depth of the fluid effectively, you pick up an extra factor of h in here. So you get this combination of the total thickness and then times the surface slope. And then you've got this resistance by basal stress on the bottom of the ice sheet. So we have an equation of motion, and in principle now you could take this, use it to calculate a velocity, calculate a flux by multiplying by the thickness or integrating over the thickness. And then everything you could run through and run a model of ice sheet flow. So just before doing that, just want to pick out to explain a little bit about how the force balance works. And in particular, do we need to worry about this stress term at the bottom of the ice sheet? So if we put in some values, so we say the density of ice is at leading order around 900 kilograms per meter cubed. So 917 is slightly more accurate, but for a scaling estimate, this will do. The density of air is negligible compared to the density of ice. We mentioned at the start that these ice sheets can be about 1,000 meters thick, and a characteristic fast ice flow velocity. So I'm going to try and estimate a relatively fast acceleration, might be 10 kilometers per year. And you might see fluctuations in the ice speed on a timescale of order years. And the surface slope, d eta dx, is of order 10 to the minus 3 is a typical scale. It can get a little bit steeper than that. You can probably be slightly shallower, but in many places on the ice sheet, you're not going to be orders of magnitude, many orders of magnitude shallower. So if you take these numbers and plug them in with an estimate of gravity, just to give you rough order of magnitude estimates. So this basal stress is quite hard to fully estimate, but you can calculate the other two terms in the equation. So if you estimate the inertia, so basically, or inertia per unit area, but basically the density of ice times the thickness, and then because we divided by area, so the thickness is the volume per unit area, and then multiplied by the acceleration. That has magnitude of about 10 to the minus 5 kilograms per meter per second squared. So the odd units are because I'm using thickness rather than total volume in here. And then we can calculate this driving force comes out as being 10 to the 4 kilograms per meter per second squared. So with this particular estimate, you've got a gap of about 9 orders of magnitude between the acceleration and the driving stress. And you can play around a little bit with some of these estimates, but you're not going to close, for realistic ice sheet conditions, you're not going to close a gap of 9 orders of magnitude. So you end up with this driving stress term is going to be much larger than the acceleration. So the acceleration of these ice sheets is negligible. And for those of you who've done some fluid mechanics, this means you've got a low Reynolds number flow. So you could have estimated the Reynolds number at the outset if you had an idea what the viscosity is. We've come at this from a slightly different angle here. And the other phenomena that you get is you find that the driving stress is basically balancing the basal drag, is the conclusion that you have to draw. So in order to satisfy this equation, you must have relatively large basal drag. So this becomes a little bit of a problem because this is probably the hardest thing to quantify in this particular budget. So everything here is something that you can estimate from observations. It's also something you could predict from a model if you knew what this basal stress was. And this is actually an area of open research, is trying to understand a little bit about how you should describe the basal stress. So is it something where the bed behaves as a plastic material? Does it shear like a viscous fluid? Is it some funky nonlinear power law fluid? And a variety of laws are often proposed, usually for making climate-related predictions with ice sheet models. An inverse problem is done where the bed friction is essentially tuned, to best match the current observations, and assumed it will stay constant over time. Some of the challenges are that if you look, so these are some pictures from a borehole that was drilled all the way through, so to a depth of 1,000 meters through one of the ice sheets in Antarctica. And this is what the ice looks like, slightly above the bed. So this isn't actually below the bed. This is actually ice here, but as you can see, it's filled with sandy type of sediment. So you've got quite a complicated problem going on at the bed of the ice sheet. So you've got this mixture of ice and sediment. There's also potentially water thrown into the mix too. And one of the key questions, particularly in Greenland of interest, is understanding how meltwater drainage to the bed can lubricate and change the basal drag forces on the ice sheet. So that's one area of particularly key interest. And the other thing I should mention is in everything I picked up before, I didn't really pick up anything about the viscous deformation of the ice. So to do a better job with modeling the ice flow, in some circumstances, we also need to account for the viscous ice deformation too. Right, okay. So I'm going to switch gears and go back to a slightly more phenomenological picture for the last little bit of this lecture. And we're just going to think a little bit about some of the other driving factors. So the first thing we're going to think about is how might the ice sheet respond to climate forcing? So we saw that this comes in through this net accumulation minus ablation term. So snowfall minus sources of melting and perhaps carving of icebergs. And a natural question you might ask is, would you expect ice sheet to decay to depend more sensitively to atmospheric or ocean warming? So if often you would expect there to be, as the atmospheric temperature changes, the ocean temperature is likely to change with it by a similar order of magnitude. And one question of interest might be, if you change both the atmospheric and the ocean temperature by the same amount, which has a more significant impact on the ice sheet? So we can look at this, get some insight into this using a very simple experiment. And I gather some of you may have seen this kind of experiment before, but we'll just run through just to use to try and attach some of your physical insight. And for those of you who've seen some thermodynamics, you can probably do a more detailed calculation. So I'm going to get you to think about the following question. So we're going to set up an experiment where I'll show you a time-lapse video where we've got various different icebergs, which are actually just ice cubes that I've formed by mixing some blue food coloring with water and putting this into the freezer. So the blue food coloring there is to make them easy to visualize, and also you can see where the water goes. And we're going to put these ice cubes at the same time into either a cup containing air, so simulating ice melting in air alone, a cup containing salty water in the middle, and one containing fresh water to the right. And these have all been left, in the experiment, they were all left to equilibrate to room temperature before things start off. And what you might think about is, which of these do you expect to melt the fastest? So just have a little bit of a think to yourself. So what your physical intuition tells you about which of these will melt the fastest. And we'll do the experiment. Somebody has set up a poll in the whilst we were talking. Excellent. So you might have a think through about what you think will happen. So we'll let the poll go. Okay, so you can keep the votes coming in whilst I just set up explain how the experiment's going to work. So we basically got these three different containers. I've got some ice cubes that I'm going to drop in, and we're going to drop them in and let them go. So we've got 72% of the people voting. The most popular option is salt water so far. Some people may be waiting to cast their vote whilst they watch the video. So we can let that go. And you can see the ice cubes are melting. So this is sped up around about 50 times, just because we don't want to wait 20 minutes. And you see in this particular case, the freshwater ice cube melts marginally faster than the ice cube in air. Sorry, than the ice cube in the salt water. But both of these are melting substantially faster than the ice cube in air. So you might look a little bit at these. So we had one. In the poll, we had one right answer. So congratulations to whoever picked that out in the poll. And so a majority basically thought that it would melt faster in salt water. So this is a slightly cheeky comparison for me to ask you. So the answer actually depends a little bit on the size of your container in this particular case. So the saltwater answer is actually more relevant to the ocean, and also the typical characteristic temperature and salinity ranges you see in the ocean too. So this is a lot warmer than you'd find in the Antarctic seas. Right, okay, so we can understand a little bit also about why this is melting faster by looking at what's happened to the colored water. So you saw that the dye is spread throughout the cup on this particular case. So for this particular experiment, you're in a setting where if everything is entirely fresh, effectively the cooling of the fresh water by the ice cube for these particular conditions generates relatively dense fluid that's able to flow and mix in the tank and basically transport all of that heat away. Whereas for the freshwater case, all of that water was fresh compared to the salt water, is relatively buoyant and because it has lower density, and then rises up to the surface. And the fine scale details of this balance due to the size of the container meant that the mixing was more efficient in the case with the fresh water, because the thermal convection could drive through the entire depth rather than just only pulling up at the surface. Okay. So the lessons we learned from this can give us some hints about how ice sheets respond to changing conditions. So we've got a hint that they're likely to respond, given equivalent warming, they're likely to respond more significantly to ocean forcing. And on this particular plot in here, there's a lot of information in this plot, but I'm just going to pick out the key features for you. So this is from a paper by Pritchard and co-authors, based off a huge amount of observational data, but I'm just going to pick out the key features. So on here, there's a red to blue color scale around in the ocean, around the continent. And this is showing you the temperature near to the seafloor in the regions where the water would be able to get into contact with the ice. You also have on this setting, there are regions, there's a separate color bar on the regions where you have floating tongues of ice. So this blue, yellow, red color scale. And what you see is that the regions on the red part of the color bar where you've got relatively fast thinning of the ice tend to be concentrated in this West Antarctic region rather than the relatively slower thinning, or perhaps in some places even thickening in some other parts of the continent. And this associates with the regions where you've been able to get warm, relatively warm waters that I'm going to call warm here is 1 degree C, relative to the -2 degrees C or so in other locations. You've been able to get this warm water up towards the ice sheet margin, and it's basically been able to attack and melt away at the ice sheet. So the other bit of information in this plot are, you can see there are lots of little lines separating out separate basins. So these are drainage basins where the ice flows out into a particular region. And the area of this gray circle is basically proportional to the mass discharge out of this particular drainage basin. So you see also the fastest discharge of the grounded ice is also located in regions where you've got substantial thinning at the margin of the ice sheet. So this could be via direct melting. And one of the take-home messages, so from that simple experiment, is that you end up with ice melting faster in water than it does in air at the same temperature. And if you think about the thermodynamics, you can understand that by the fact that water has a much larger heat capacity. So it's able to carry more energy for melting, given an equivalent change in temperature. And then this energy for melting is able to drive faster ablation from below. So this means that there's a significant vulnerability to ocean warming. The other thing we saw from our little ice cube experiment is that the water flow can be quite important for impacting how fast the ice melts. So the reason for this is that you can basically, if you're able to remove the cooled water away from the surface and replace it with warm water coming in, you generate quite a substantial what's called a turbulent heat flux in towards the ice face. And this is another area of research, is trying to understand the circulation of water around the ice sheets, and then also how it gets up very close to the ice sheet and actually drives the melting. So I'm just going to probably finish up by just showing you a simulation where we're looking at a simulation of a slightly idealized problem, but to probe some of the dynamics of the ocean flow very close up towards the ice sheet. So this is interested in understanding how quickly is heat transferred in towards the ice, but also where does that meltwater go within the ocean? So does it all rise up to the surface, such as we saw in our cups of water at the start? Or can you have more complex circulation, which could have key impacts for how you change the ocean structure? So I'm going to show you a simulation in a second that comes from a setting where we've taken a very idealized setting where the salinity is varying with depth over a scale of a few meters is the simulation I'm going to show you. These are two-dimensional simulations of the Navier-Stokes equations. And we're going to look at what happens when an ice is basically melting into salt water with a salinity gradient. So the salinity is varying with depth, so it's relatively fresh and has low density to the surface and increases further down. And one of the quite curious things that happens is rather than the water rising all the way up to the top of the tank in this particular simulation, so rather than getting persistent rising of the water, what you find actually happens is as this turbulent flow develops, it starts to generate some pattern formation. And there's a characteristic length scale that parcels of water are able to rise. So you can understand this by looking at the mixing with the background fluid and how far that parcel would rise before it reaches a neutral density level, where it's at the same density as the background, and then it flows out into the background. But this kind of gives you rise to a potentially counterintuitive effect where actually rather than that fresh meltwater rising right to the top, the mixing and interaction with the background stratification actually gives you layered outflows at depth. Okay, so I should probably skip ahead. So I'm unfortunately going to have to cut without the marine ice sheet instability, because I think we're running a little bit short on time. But I'll just leave you with some broad conclusions. So we mentioned at the start that the Greenland and Antarctic ice sheets are a key uncertainty for predicting future sea level. We looked at how to model ice flow, and it was driven by gradients of hydrostatic pressure that are linked to the changes in the thickness of the ice, or the surface slope in particular, and resisted by basal drag. And there are various uncertainties. So one of these is how the ice shelf melt, depending strongly on ocean flow and temperature, how those effects couple together to control the impacts on the ocean forcing of the ice sheet melting. And another key uncertainty regards the basal drag, so how the friction behaves on the bottom of the ice sheet. But I'm out of time, so I should probably finish up there and leave it there. Thank you for listening.
Thank you so much. Thanks also to everyone who came. This is your chance to ask questions. So either pop them in the chat, or if you want, we don't have that many people here, just unmute yourself and ask your question.
Well, if nobody else is going to start by asking one, so I know you talked about that it's basically just the slope at the surface and not the slope of the ground, which makes a difference for the flow of the ice sheets. But if we think about something like isostatic rebound, if it's being caused by ice sheets melting, presumably it would also lead to a greater slope of the ice sheets afterwards. So could that lead to some type of feedback loop?
Yeah, so you can get a little bit of a feedback loop due to isostatic rebound. So I won't run through this, but I'll just use the picture actually on the previous slide. So this ties in a little bit to something. There's a marine ice sheet instability, and there can be an effect due to isostatic rebound. So for those of you who don't know what isostatic rebound is, so this is basically the Earth and the bedrock underneath the ice sheet is also deformable if due to the weight of the ice. So as you can see in many of these pictures, cartoon sketches that I drew, often, and also the cross-sectional observations, often the bed of the ice sheet actually dips down substantially below sea level. And this is likely due to the weight basically of the ice pushing the bedrock down below sea level. So this is a process that there's a rapid elastic part of this, and there's a very slow viscous deformation. But as you start to melt the ice, the elastic part of that in particular gives you quite a rapid adjustment of the bedrock back upwards, and that can lead to some feedbacks on the surface elevation. That's it. It basically moderates a wider feedback where you can end up, so there's an instability that kicks in where you have the bedrock of the ice sheet gets deeper as you go inland into the continent. And what happens is if the ice starts to retreat slightly, you end up in a setting where to reach the point of flotation, because you're in deeper water, you have to be at the point where you're just floating, you have to have a larger thickness of ice. And then where you have a larger thickness of ice, some more detailed modeling shows that gives you a larger flux of ice out into the ocean. So you can get a runaway feedback where the retreat of the ice basically leads to faster discharge, which then leads to thinning in that particular region and further retreats, or a loss of mass off the ice sheet and then further retreat. And that kind of has an interplay with the glaciostatic rebound that you're talking about. So the surface of the Earth moving up and down as you remove the weight off the top.
Thank you.
Cool. Any more questions?
You're welcome to either say them yourself by unmuting yourself, or you can type them in the chat.
I have a question.
Yes.
When you study this kind of phenomena, how many of the things you do is based on like empirical data, and how much of them is like, as we just talked about, the like analytical solution of stuff?
Yeah, so I guess there's a question when I work on this topic and when people in the field work on this topic. You might get slightly different answers, because this is one of these topics that a lot of the research questions, they kind of sit at a boundary between different fields. So there are people with earth sciences backgrounds and geologists interested in understanding, and glaciologists interested in understanding these phenomena too. So you can often make quite a bit of physical understanding into processes using these slightly idealized models. So simplifying the models down and stripping them down a little bit. And also things like the fluid flow model that I showed you before, thinking about simple toy problems. You can often understand physical processes and feedbacks in these settings. If you want to make a quantitative prediction, you often need to, at that point, feed in more empirical data for certain things. So here with this scaling, the argument I went through, I gave you a hint that the bed stress is important, but I didn't tell you what the bed stress, how that might depend on the velocity of the ice, the thickness, the pressure, the amount of water that goes to the bed. So those are the things that are not very well constrained. So if you want to make a prediction, you have to try and come up with an empirical estimate of what those values are. So there's a lot of inverse modeling that's used to deal with those. So you can use both kind of approaches and they just tell you slightly different things. So there is a lot of it that is, the other bit of it is also, particularly with the ice and ocean interactions, it's very hard to think about every single possible process from a theoretical perspective. So often the observations really can guide how you might start to model and think about writing down physical theories for these systems. So you can, there have been periods of times over the last couple of decades where basically, because of the scarcity of observations right up close to the ice, you observe something new and it completely revolutionizes your way of thinking about the problem.
Okay, thanks.